Let's get started. Better late than never. Any questions? Okay. So, when I was thinking about this, I kind of rearranged what I was planning to do a little bit. So I realized I was kind of accumulating, examples and results specifically about curves. So I wanted to start the discussion about curves, which are kind of the most concrete application of the stuff we've been talking about, and then talk about cohomology on Wednesday, when we've motivated it a little bit more when trying to solve problems with curves. All right. So what's a curve? So for my purposes, over K, I'm just going to assume that K is an algebraically closed field. Make my life easier. Most of the stuff I'm going to say, you can do it over a non-algebraically closed field, but you have to think about everything a little more carefully. I don't need that noise in my life. All right, so that means a 1D integral scheme. Okay, of finite. So we could call this a 1D K variety. And depending on how you like to define variety, you might want to include the word integral or irreducible here. Yeah. Oh, I should have, yeah, sorry, I should have added separated, yes. Okay. Cool. So we know one very important example of such a thing, which is P1. But we've already talked about P1. We know all the line bundles. They're all of the form O of K. And we know that O of K for K positive are all very ample. They all correspond to embeddings into projective space, with O of 1 in particular corresponding to the identity map from P1 to itself. All right, so P1 is a very important object, but for the sort of questions we want to ask, it's kind of already known. Okay. So now let's think about a slightly more interesting curve. And what I want to think about is look inside P2 at the vanishing set. I believe this is exactly the guy we used on our homework, but it doesn't matter that much. Minus x cubed plus z. All right, so usually people would write y squared equals x cubed minus x, and putting the z in here to make this homogeneous. So I'm taking the closure of this guy in P2. So this would give me a curve inside A2, and now I'm taking its projective closure. Oh, sorry, z squared, yes. All right, so how do I think about line bundles on this guy? Well, I know how to define line bundles. I have to choose a divisor. What's a divisor on a curve? On a curve, that just means a formal sum of points. I should say a Weil divisor is a formal sum of points. A Cardi, an actual line bundle, right? Remember what we discussed last time. When I have a Weil divisor, I can look at this sheaf O of D, and if D is locally principal, then this is a line bundle. For simplicity, we'll mostly focus on the case where the curve is regular, in which case every divisor is locally principal. Right? If C is regular, that means every local ring is a DVR. Right? And so locally DVR. And so indeed, if I have any point, I have C, this sort of draw this as a disk because I'm thinking about the complex world, in which case this would be a two manifold. I have a point here, right? And when I ask, is this divisor locally principal, the thing I'm asking is the corresponding prime ideal in the local ring principal? And that's exactly asking that the local ring is a DVR. So the divisor, which is just one point, is locally principal. Now, of course, not every divisor is going to be principal on most curves, right? So we saw on P1, and P1 is regular, so its local rings are all DVRs. Every divisor is locally principal, but there's a global invariant that divisors have that might stop them from being principal, which is summing up how many points are there in the divisor. And more generally, if I were working over a non-algebraically closed field, I would have to weight by the degree of the extension of the residue field. And I'm using that I'm algebraically closed. So every point is going to have residue. Every closed point is going to have residue field K. More generally, it would be a finite extension of K because we're finite type. Okay. Cool. Well, the question is, if I have some curve which isn't P1, and trust me, this is not P1, we'll see why in a moment, is there some more sort of sensitive invariant to what's going on? And I'm going to ask you to trust me on a few statements I make, but okay. So let's try and think about some of these line bundles and sort of figure out if we can get a map to projective space that's interesting out of them. So what happens if I look at O of P? So here I'm using the divisor that's 1 point. So let me remind you, what is this? This is the line bundle whose sections are rational functions. So I'm identifying its sections with rational functions that satisfy a condition on their valuations. So what I'm looking at, I would be writing Y here, but I should just write P, the valuation of F at P. So that's the order to which it has a zero or a pole at P, plus, let me write this out for general divisor first, This is going to be a sum of the classes of points. So I require that at this point, I get a positive number when I add in this AP. So if I were looking for, so for example here, right, on P1, every rational function has some poles. So whether a rational function gives me a section of this guy's, whether these guys cancel out the poles, and I should have a dependence on U here, this is only for P and U. I'm checking whether something is a section over U. Okay. So if I look at O of P, the way to think about sections of that is I can think of that as rational functions that have, at worst, a pole of order 1, P, and no poles anywhere else, no other poles. So I don't expect you to give a detailed proof of this because it takes a little bit of work, but you can convince yourself, try to write a rational function, and rational function really means take polynomials in X, Y, and Z, right? Modulo this relation and look at ratios of them and try to find one. So you'll convince yourself right away that you must have some poles because there has to be something in the denominator. Unless you're just going to be constant, but try to make one that has a pole of order 1 at one point, and you'll fail. So it turns out that actually, this is the same. Sorry. If I take the global sections on this curve, this is my C of OP, I just get my base field K. I only have the constant functions, and there's no global one. Now, once I remove a point, then it's sort of free for all. Actually, so one of the things we'll prove a little later is that once you remove one point from a projective curve, you actually get something affine. So if I remove one point, there will be lots of possibilities by sort of pushing all of the poles onto the point where I pulled out. But globally, I can't do it. I can't only make a pole of order 1 at one point. On P1, I can do that, right? So on P1, basically, I can say, oh, I'm going to have, X as my denominator, and then I can put AX plus BY in the numerator, and I get a two-dimensional space of sections of O of P. This is isomorphic to O of 1. But here, if I take a linear function, it's going to have generically 3 zeros. And this is where I get into trouble, right? Because if I try to put all the zeros of a linear function at one point, it will vanish to order 3 on this curve because this is a cubic equation. Yeah. Every divisor, you're asking, yes, it's a finite sum. Yeah, I mean, we're not doing analysis here. There's no such thing as an infinite sum. All right. So one interesting thing that this tells us, right? So we have one section now, and we're interested in, for example, is this line bundle globally generated? right? If I took the trivial bundle, that would be globally generated. There's only the space of constant functions, but the constant functions generate. And you might think the same thing happens here, but writing O of P, I have to be careful about what the stalks are. So right, globally generated means if I look at the map from global sections to the stalk of O of P at some point X, that the image of this guy generates this as a module over the local ring O of C. And how should I think about this stalk? Well, I go here and I look at this and I say, oh, okay. When I look at this stalk, I'm only getting the condition that comes from the point P, right? So what I get here is the local ring, and then I'm allowed to have a zero or a pole depending on what point I'm. So in this case, I would take a uniformizer and I would raise this to minus delta xp. So more generally, if I look at O of D and I look at its stalk at a point X, that means I look at the local ring, but I'm allowed to have a pole. Or if this guy is negative, I'm required to have a zero. So more generally, I'm going to be raising to minus whatever the coefficient of this point in the divisor D is. So in particular, a rational function generating the stalk at a point means it has no more zeros than you require, right? It's sort of as bad as you can imagine. If you're allowed to have a pole of order 2, it has a pole of order 2. If you're required to vanish to order 2, you vanish only to order 2 and not to a higher order. So if I'm going to generate the stalk at this point P, I have to be, when I think of this guy as a rational function, I have to not just not be zero as a rational function. I actually have to have a pole of order 1 because I'm allowed to have it. Okay. So OP is not globally generated. And this shows us something actually pretty interesting, which is that O of P is not isomorphic to O of Q for all P and Q, because P is distinguished as the point where this guy is not globally generated. Right? This map to the stalk is surjective if and only if X is not P. Sorry, I should say it generates. So these guys can't be isomorphic because this guy has a section that generates the stalk at Q. This guy doesn't. This guy has a section that generates the stalk at P. This guy doesn't. All right. So this guy is not base point free. So it doesn't give us kind of a well-defined map to projective space defined on the whole curve. I have to remove the point P to get the map out of this guy. All right. Now, what happens if I look at O of P plus Q? Or better yet, actually, let me think specifically about O of 2. All right, it turns out that this now has a two-dimensional space of sections. So this is going to induce and is base point free. So this is going to induce a map from C to P. And let's try to be concrete about this. Let's think about the case where P is 0, 1, 0. So usually when I look at this curve, I would draw like the real points, and I would see something like this. So 0, 1, 0 is the point at infinity that's off in this direction, which is of course the same as off in this direction. Corresponds to a vertical line. And you can of course check that 0, 1, 0 satisfies this equation. So if I set z to 0, it's the only solution because x is required to be 0. All right. So the reason I like this guy is it's sort of well suited to our chosen embedding. So if I look at z, what is z? It's a section of the pullback of O of 1 from projective space. Right. So as a section of a line bundle, I haven't even told you what the line bundle is yet. I get vanishing to order 3 at this point. So again, you can check if z is 0. I just said that. This is the only point on the line at infinity, right? Z equals 0 is the line at infinity for this picture. And I only get one point where it vanishes. And because this is a cubic equation, it vanishes to order 3. That comes from the x cubed here. On the other hand, if I look at the divisor of x, so x also vanishes at infinity, but it vanishes at another point here. Right, I'm looking at the x-axis. So the x-axis has a point of intersection of order 1 with the line at infinity, and it's exactly at this point. And it has an intersection of order 2 with the curve here because it's a tangency. So I get P plus 2 times the origin, which is 0, 0, 1. All right, so this tells me when I look at x divided by z, then that's a rational function, and its divisor is minus 2p plus 2, 0, 0, 1. And of course, this would have worked with any function that vanishes to order 1 here. So I can find other rational functions which also give me sections by looking at x plus z divided by z, different coefficients. So at least for this point, we see that indeed we get a two-dimensional space of sections. And you'll have to believe me that there's no other way to do this, but I promise you it's true. So I get a map from C to B1, which sends x, y, z to the point x, z. And a point here is generically going to have two pre-images because I get this quadratic equation in y. If I think about it in terms of this picture, it's projection onto the x-axis. Of course, I'm only seeing the real points. There are complex points that will project to this part of the x-axis. All right. And then I see here, oh, the actual embedding of this guy is an elliptic curve. And not to P2 corresponds to, I mean, this is kind of dumb. I'm just going to be writing the identity here. This uh, and I want to emphasize here, there's nothing sort of special about this P, right? This is we know this is an elliptic curve. So we actually know there's an automorphism sending P to every other point of the curve. So there can't be anything special about one point, but we also know that when we want to think of an elliptic curve as a group, we have to choose a distinguished point, which will be our base point. All right. And I should get a move on. Probably spent half the class on this. Yes, I have. So maybe just to connect back to the usual addition on elliptic curves, I had mentioned this previously, but we're sort of starting to see a little more why it might be true. If I look at pic of C, what I get is isomorphic to C itself times Z. And the bijection is that if I take Cn here, this maps to let me call it P. So I choose some distinguished base point, which we usually call 0. I get P minus 0. That's when Z is 0. That's an isomorphic to the degree 0 things. Plus n times this base point. So in particular, this thing about getting, I should maybe mention, I don't know whether I've said this yet, the degree of a divisor on a curve is just the sum of these APs. So here I was talking about a divisor of degree 1, 2, and 3. And so in particular, this fact that we got all these different line bundles, this is just, if I look at P comma 1, that maps to P itself. All right, and then where do I get the addition law on the elliptic curve? If I look at some linear function, ax plus by plus cz, divided by z, that's a rational function, and its divisor is the sum of the intersection points. So P1 plus P2 plus P3 minus 3 times 0. Right, so the 3 times the base point comes from dividing by z. The other guys are the intersections of this elliptic curve with the line ax plus by plus cz equals 0. Uh, yes, right. I mean, these don't have to be three distinct points. All right, so this is why if I send E to this difference, I get a group homomorphism from the usual definition of the elliptic curve group law using lines to the group law in K. Okay, so what else do we have to? So this was working with one particular curve. And you could imagine, okay, I gave you this curve in such a way that it was obviously projective, and I was using how it was embedded in projective space to do calculations. But you could imagine, what if I just handed you one of these? All right, so what if I got a curve in a way that wasn't obviously projective? What would I do? Well, I could still sort of do this analysis of start looking at divisors where I allow things to have some poles. And, presumably I know an open affine inside this curve, so I know what its function field is. And so I can just start sort of going through this and try to find a map into projective space by just taking some big divisor, allowing myself to have lots of poles. So in fact, if C is a curve, C is birational to a projective variety. In fact, this won't be completely obvious in the proof. It might be kind of obvious in the proof. Um, in fact, there's sort of a canonical choice of projective curve, not necessarily with a canonical projective embedding, that this guy will sit inside of. Um, okay. See what we say. Okay, so let me just give you a vague hint of how one proves this. The first thing we know is we have a U inside C, which is an affine curve, an affine one-dimensional variety. And we know an important thing about affine one-dimensional varieties, which is they have finite maps to A1. Okay, by Noether normalization. So I can think about this map to A1 as a function. So basically what I'm doing here is I'm grabbing a pretty generic function on my curve. If I try to extend it to C, I just need to think about it as a rational function. And so then what do I do? Well, it turns out that I can now Okay, so I think about the rational function from C to P1. So I call this guy T, that sends a point to 1 colon C of C. All right. And we can now use this map to P1 to define this projective guide we're looking for. So somehow the way I really should be doing this is I should be taking a relative spec. I will describe this implicitly, and you can think about it in terms of gluing. So I'm going to define a scheme C of U for all affine opens inside C. Sorry, affine opens. So maybe I'll just call it V. Avoid confusion with the U I had before. All right, if I have this affine open in P1, what can I do? Well, I can take its pre-image under this map. Let me call this pi. And take pi inverse of U. Look at functions on there. And so that's a subring of the function field of C. And I can do something interesting in the function field of C. I can take its integral closure. Not paying enough attention to my notes and being bad. So I have this map to P1. I can take functions on P1 and pull them back. Just have to like literally write what's in my notes. Somehow I'm struggling with that. So what am I doing? I have this map to P1. And on P1, I have a notion of functions not blowing up at points on P1. So I take the functions on P1 that don't blow up anywhere in my V. I pull them back to functions on C. And well, maybe there are some poles or something, but they're well defined as elements of the function field. Okay. Now I take their integral closure. I should note here, right, this map, because it's finite over A1, this means that C contains inside it the function field of P1, which is the same as the function field of A1. And that's a finite field extension. Right? So C is pretty close to P1 in the sense that I get a finite field extension. So now take integral closure of this guy. So what am I really doing here? I'm defining a sheaf of algebras on P1, and I'm going to take its relative spec, which just means, so let me call this integral closure A of V. So now I'm going to take relative spec, which just means take spec of AV for all V and glue in the obvious way. Right. That's going to give me something that's projective over affine. So, sorry, that's finite over projective. Um, so there's a hard theorem that, let me call this relative spec C prime. The hard theorem that the map from C prime to P1 is finite. All right, this is not obvious. It's proven in Verkeil, but requires a little bit of thought. So basically what I'm doing here, I'm doing what's called a normalization. I'm taking my ring and saying, gee, I wish it was normal. And I kind of force it to be normal by taking integral closure. But I'm doing something a little bit stronger because I'm saying, gee, I wish it was normal and it was finite over P1. So I'm not taking the normal closure, the integral closure of all functions on C. I'm taking integral closure of the functions on P1, which is sort of forcing it to be finite over P1. Yes. Yeah. Because a rational map is a map on a finite open set. I'm assuming that my scheme is integral. So that's the definition of a rational function. All right. Clearly, I've kind of mangled this proof, so I think I'm just going to make things more confusing if I push it further. But the key point here is, so the function field of C prime is the same as the function field of C, so they're birational. And the pullback of ample line bundle by finite map is still ample. And this is easier to see if you think about this topological version of ampleness, right? One way to think about ample is that you can invert finitely many sections of powers and get affine guys that cover your space. So in this case, right, there are two functions on P1, I can invert and get affine guys. Their preimages under this finite map are still affine. Finite maps are always affine, right? So exactly the same sections give me sections of the pullback of this line bundle, which give me a cover by ample guys. But this is one of these points where having these different characterizations of ample can be very helpful. All right. So there are various extensions of this, which we can definitely don't have time to go into. Improvements. If C is regular, then I can choose things. So C mapping into C prime is an embedding. If C is proper over K, remember properness is kind of the replacement for compact, then C and C prime are just equal. I should say regular and proper. So if I have a proper regular curve, and I actually don't need regular, but let's not worry about that, then it's automatically projected. And this is something special about curves. This doesn't happen in other cases. So there are lots of proper non-projective varieties. But none of them are curves. All right, cool. So how does one prove that? Well, there are various ways of thinking about it. But of course, what we should be looking for is to try to prove that if we have proper smooth curve, then it has an ample line bundle, or better yet, a very ample line bundle. So now assume C is proper. Oh, am I completely out of time? Ooh, yeah, completely out of time. Okay. Well, let me just state this now and we'll talk more about it next. Um, so given a line bundle, and I want to ask, is it base point free? Is it very ample? And of course, if I know the answer to that question, I can then later figure out, is it ample? Um, and there are nice ways of thinking about this criterion of being base point free and ample, which is, well, what does it mean that I'm base point free? It means that I have a point that's non-vanishing everywhere. And so it means that if I take L minus P, that by definition is L tensored with O of minus P. So I'm forcing my sections to vanish to one more degree at this point. Then I should lose sections. So I have a natural map from sections on C into here to here. Let me call that iota sub P. And I'm base point free if iota sub P, which is obviously injective, is not surjective. For all P. All right, and there's a similar characterization of very ample, which we'll discuss more next time, where you look at 2 points and require that you drop dimension by 2 when you remove those 2 points. That tells you those 2 points are mapping to different places. And similarly, when you double a point, that's basically checking with the derivative at that point vanishes. So you can characterize all of these things in terms of what's the rank of this map? But then that raises the question of how are we going to figure out what the rank of this map is? All right, and on that mystery, I will leave you.